Okay, so I'm going to get started. So today, now I'm going to say it again so that I'm on camera. If you have the digital copy of the book that's floating around, chapters 10 and 11 are switched. Read the section on interiors, not the one on the sun. If you read about the sun, you have another reading to do. Oh, now I got to say it again. Somebody tell Ashley what I just said. If you read the digital copy of the book, chapters 10 and 11 are switched.
Oh, I do.
But I think that you're set. Yeah, but I think you're sorted. So okay. Now I'm going to talk about the interiors of stars. So I'm going to stop talking about. Where's my eraser? So I'm going to stop talking about atmospheres, and we're going to start talking about the interiors. So we do atmospheres first. Oh, you know, man, whatever they did, cocked up the boards. This is terrible. So we talked a lot about how light passes through. You guys good?
Yeah, sorry.
So we talked a lot about how light passes through the atmosphere of the sun, and that was kind of a challenge. And now we're going to talk about how the light is produced inside the sun, and this is harder because it's messier. So I'm actually going to do things backwards from the way the book does them. So that I can set the stage. So when we're talking about stellar structure, there are 4 equations. And I'm actually going to give you 6 because one of them has 2 ways that it might go, and then you need a 5th thing to close all of the system of equations. So the system of equations are by name, they're mass conservation, let's call this force balance, this is equivalent to hydrostatic equilibrium, photon production, and heat transport. So we have these 4 equations, and they're all kind of gnarly, and they're all coupled together. So we have 4 ordinary differential equations. We're going to make them ordinary differential equations instead of partial differential equations because that way we can actually make some progress. If they were 4 coupled partial differential equations, it would be much harder. So we have these 4 equations, and I'll write down what they actually are. So these are the 4 differential equations that underpin everything. The heat transport equation is actually 2 equations because sometimes you have convection and sometimes you don't. We'll get to that. And then the 5th thing that we need is the equation of state. And so typically we use the pressure as PV equals nRT, which we're going to do for everything in this class. We're not going to do anything more complicated than that. But PV equals nRT is only kind of true. So we need an equation of state that says that P equals some function of density and temperature. Often we'll just use rho KT as the ideal gas law. So these 4 things all fit together. So the first equation tells me where the mass is. So they're all all 4 equations are spherical. So they're one-dimensional equations where the radius is the only dimension. The 1D radius is the only 3-parameter. In reality, a star is a 3-dimensional structure, and these should be 4 3-dimensional partial differential equations, and it's a lot harder, and you have to use a computer to solve it. You have to use a computer to solve these anyway. We're now in the part of your physics career where there are very few solutions that you can just write down. Okay, so the first equation is mass conservation. So I'm going to write them all down I'm going to derive the first two today, and then we'll spend next week deriving the second two. So mass conservation is relatively straightforward. This just says that m equals the integral from 0 to r of rho dv. Don't write that one down. Well, okay, write that one down, but I'll circle in big numbers or in big squares what the real equations are that I care about. So mass is just the integral of rho dv. That makes sense, right? So if I rewrite this, and now we're going to assume that everything is spherical, that means there's no theta phi dependence on anything. So then this becomes 0 to r of rho times what? What's the spherical version of dv?
R squared sine theta dr d phi d theta.
Yeah, so you got r squared sine theta dr d phi d theta. So that's dv.
I'm sorry, I was thinking about another homework and I realized I did something right. So
No worries. I couldn't quite tell if that face was, oh my god, I have no idea what he just wrote.
I think it's sine phi.
It might be sine phi.
yeah, sine phi.
It's sine theta.
It
I can decide which one it is based on how I draw the coordinate system. This is correct if I have drawn the right picture. This picture is which? So I got my three-dimensional coordinates, so we'll call this x, y, and z, or r, phi, and theta. One of these is phi, and one of these is theta. So one of them is the angle coming down off the z-axis, and one of them is the angle going around.
Well, the sine has to be the one off
The sine is the one off the z. So I typically call this theta because I'm a physicist. If you're taking a math class, they flip them. So universally, it's the other way around. And because of that, I can never remember which way it is. So the sine comes off the one that comes off the z. So draw the right picture. Now, this angle goes from what to what? Phi, theta, that comes off z.
0 to pi or 2.
This one just goes 0 to pi. It goes all the way down.
Oh.
Down. So it goes all the way down to that. And then the phi integral goes from 0 to 2 pi. When I do both of those integrals, I'm just left with 4 pi. So all of this comes just to 4 pi r squared dr. So I can do two of those integrals because I'm assuming spherical symmetry. I'm assuming that there's no dependence on theta and phi on any of my quantities. So this is just a round star. So now I'm going to take a derivative of this because I have an integral equation. And you take a class on differential equations. You don't take a class on integral equations, right? They're worse, all right? It's not as well defined of a field and the methods are harder. How do I turn this integral equation into a differential equation? How do I get rid of integrals?
Derivatives.
With derivatives. So what do I do to this equation?
Take the derivative of both sides.
Take the derivative of both sides. So I take the derivative of both sides, and I'm left with dm. This is now the full derivative with respect to r. The subtle details with full versus partial derivatives are not yet a nightmare in your head, but they will be right now. I'm just being clear. This is the full derivative, not the partial derivative. This is dm dr equals what? What's the derivative of this? It just kills the integral. It's just rho of r times 4 pi r. Notice I use a capital R because it's the upper endpoint is what you plug in when you take the derivative. Does that make sense? That's how fundamental theorem of calculus works. So the first equation is this. I'm going to write them over here. Let's write them over here. Mass conservation says dm dr equals 4 pi r squared rho. That's it. Oh man, I wrote that too big. I'm going to have to use both boards. I'll just use both boards. Okay, so mass conservation. So this one's pretty straightforward to understand. Mass is conserved. Mass and density are related to each other. Kind of a dumb equation to write down, but I have some things that depend on mass and some things that depend on density, so I need to have an equation that relates the two things. Okay, force balance. Let's talk about force balance for a second. Force from pressure is what? If I have I have a cloud. It's messy. It has some pressure field. That's a complicated function of position.
Cool.
What force is this pressure field going to give me? How do I get a force from this pressure field?
Derivative.
That's a great guess. Derivative with respect to?
X.
Yeah.
Considering it's defined in X.
Yeah, not X. We'll use nabla.
Oh, okay.
What's the relationship between nabla and d by dx?
It's gradient.
Well, what is the gradient? What is this thing?
Isn't it the maximum derivative in every direction?
It's
Yeah,
just the
it's
derivative in
partial
every direction.
derivative
It's
in
just the
every
partial in
direction.
all three directions. You don't have to maximize it. You just take it.
Okay.
So nabla is a vector, and it's d by dx, d by dy, d by dz.
Oh, I didn't know it was called that. I thought it was just
Yeah, I don't know. Not everybody calls it nabla.
upside down delta.
Yeah.
Del.
Yeah. Its name is nabla. Other things get called, yeah.
Could you spell that? Where does it come from?
I've always just called it upside down delta or gradient.
Oh, okay.
I don't know where it comes from.
Okay.
That's not universally accepted language. It's what my Italian friends often call it. So your textbook probably doesn't call it this, but a lot of people do. It's a vector of derivatives. So it's a vector verb. It's not a noun. It does things. It's an operator. It does stuff to other things. Force is the derivative of pressure. So it's just the three-dimensional derivative. I don't care about many of the details outside of that. If you take hydro with me, we'll go into some heinous detail about how to use nabla. Right now, I just need to say that force is the gradient of pressure. Why is force the gradient of pressure? Because there are many ways to solve, to get your head around this. I'm not going to go through the way the book does it because that's a fine way to do it. If I have a sheet and I have pressure on one side and pressure on the other side, and those pressures are the same, what's the net force on the sheet? Zero. If I have a difference in the pressure, then the force is going to be away from the bigger pressure. That's really all I need right now for this. So the gradient in pressure is what gives you the force. Pressure is a scalar. Nabla is a vector. Nabla is how this becomes a vector. Then force is a vector. Okay. So force is grad P. What else is force? So I know that, man, I don't know what they did to this board. It's really weird. They certainly didn't clean it. We had postulated that they had deep cleaned the room, but they didn't clean the boards. They're in weird shape. Okay. F equals
MA.
MA.
Oh. I was
I mean, sometimes it's the obvious answer, right? Sometimes it's not, though. So F equals MA. If I have something that's in hydrostatic equilibrium, what is that? What do you think that means?
Zero acceleration.
Zero acceleration.
Zero.
So that means it's in balance. The accelerations on balance are zero. So now, when I teach this, I never write this down. When I teach this in 2048 or what's the other one?
53.
Thank you. I have a hard
I
time
don't
with
know. I
numbers.
didn't take it.
It's all good. So when I do this, I always write it this way. Because that's actually what the truth is the sum of the forces equals MA. So this equals 0 because we're going to assume that I have a spherical star that has a pressure gradient running outwards that's holding everything still. So let's work out what this has to look like. So what are the forces? So one of the forces is minus grad P. And one of the forces is minus G M. Well, okay, what are we thinking about? M is the mass of the star. I need another M. I'm going to use rho because this is actually the force per unit volume, or force per unit volume. So GM rho over R squared equals 0. And grad P, what's grad P in 3 dimensions? Grad P is just d rho dr, because the phi and theta derivatives we're throwing out by the assumption that it's spherical. Right? So this just becomes dp dr equals, I get a minus and a minus, one of them goes over there, so I'm left with 1 minus gm rho over r squared. Okay, so this force balance says dp dr equals minus gm rho over r squared. This is how the star holds still.
And rho is an expression of density?
Rho is the mass density. Yeah, that's a good. M is the total mass. R is the radius. Rho is the mass density. I'll write up the variables up there. Try anything else. G is GP pressure. Okay, so that's how a star holds still. Where did I set my notes? Where's my time? Oh, man. Yeah. Sorry, equation mistake. I forgot where I was going next. So we're going to take a second and not do the second and third equations, and we're going to jump straight to the equation of state. Because I need an equation for the pressure. So the easiest equation of state to use is PV equals rho KT over M, or PV equals nRT or little n KT. These all make sense? Let's stick with the top one. So here N is the number of atoms in moles, and R is the gas constant. Here N is just the number of atoms, and K is the Boltzmann constant. So what's the relationship between R and K? Is just Avogadro's number. The relationship between N and rho is just the mass of the particle. The book spends a little bit on talking about the mean mass, the mean molecular mass, and this is a pretty common thing that people like to use. People often like to write this as rho KT over mu times the mass of the proton, or the mass of a hydrogen, which are the same to a tenth of a percent. Where mu is the mean mass, so it's the number of, so if I have a bunch of elements with masses mi, I have mi over sum on ni. This is just taking the average of the mass. So let's say that my my star is 80% helium-1 and 5% helium-2 and, oh, actually, sorry, 70% helium-1, 24.9% helium-1, helium-2 we have 0.1%. Okay, go from there, right? So you have some fraction of mass, so then the mean molecular mass is going to be 70% times the helium times the hydrogen and 20% times the helium. So your mean molecular weight of typical atmosphere, typical outer space is going to be 1 plus, is going to be 0.75 times 1 plus 0.25 times 4. So if anybody can do that. in their head, that's yeah, so you get something like 2.75 times the mass of the proton. So the mean molecular weight, if I have 25% helium and 75% hydrogen, is going to be like 2.5 times the mass of the hydrogen. Does that make sense? So we're just averaging all the things in there. So this works just fine to just call it the mass of the hydrogen, the mean molecular mass. So this is great, but it's not very general. And one of the cool things about the ideal gas is it works all over the place, but one of the bad things about it is it doesn't have a phase change. If I'm pretending that this represents water, and I drop the temperature below 100 Celsius, this does not freeze. This does not liquefy, right? So it's clearly wrong. So if I have a more generic scenario, let's talk about that real quick. So the more generic thing, the more generic way to derive pressure, let's talk about this for a second. And this is intriguing. I had forgotten you could get the ideal gas law this way. So I'm going to make you guys do it for homework because it's more fun to do problems for homework than it is to watch me do problems. Standing by that as a sentence. Okay, so if I have, let's say I got a wall, and I have some can of stuff that's up against that wall. Why do we always use cylinders? So one of you had asked this in the reading question. Oh, I forgot to go through the reading questions. I have been forgetting to go through the reading questions, but I have been incorporating all of the things that you ask into what I say. So hopefully I'm covering all of the bases, even though I'm not explicitly going through them. If I have them here, I might talk about them later today. So why do we use cylinders for everything? Really because I need some test volume that has some radius r, because I'm going to be integrating along r or looking at things along the radius. So I need some test volume with a radius. It has to be a volume. I can't do things because I don't want to do things with differential equations. So I need to have some area around this, and the easiest thing to do is just make it a cylinder. So I have something with a length, and it's got to have a width and a depth as well, so the easiest thing to do is just make it round. So if I have particles and they bounce off this wall, what is the pressure on the wall? Well, let's talk about what is the momentum on the wall. So pressure is force per area. It's also grad P. Those are similar. So we'll come back to that for a second. Let's talk about force. So if I have a particle that bounces off a wall, the change in the force it feels is what? It's delta P over delta T. Is everybody good with that? Force is delta P over delta T, where delta P is the momentum change, and delta T is how long it takes. So P is just Px because there's only one velocity component that matters in this scenario, because there's only one direction that's bouncing off the wall. The other two directions are sliding past the wall and don't matter. So we only think about one of the velocity components for a second. This is where that 1/3 comes from, because pressure only cares about one of the velocity components. What is delta P? So F is equal to 2px in the I-hat direction over delta T. This 2 comes from the fact that I've got P going this way and P going that way, and the difference between those two things is twice the absolute value. So then how long does it take? Delta T is about 2 delta x over v, where if I call this, I have some distance in my little test volume. So it can go a distance delta x, then it has to go back. So the time it takes between times for the molecule to bounce off the wall is 2 delta x over v. So then the force is just delta p over delta t. Is you do a little bit of algebra and you get px times vx. This is vx over delta x. Does that make sense? So now, this is just one component. Px Vx is 1/3 PV, because we're assuming that the thing is basically isotropic. So I've got, so P, this is, think about this as P dot V. P dot V is Px Vx plus Py Vy plus Pz Vz. And if I assume that they're all the same, then Px Vx is just 1/3, because they're all three of those things are the same. Does everybody follow me on this third? So, now the total force is going to be the force for a particular momentum times the number of atoms I have in that momentum bit. Everybody good with that? So here's my distribution, my momentum distribution. So if I want the total force, I'm going to multiply the force for each exchange times the total number of exchanges that I have for that. And this is going to equal, let's see where we're at, do our algebra appropriately. So the total force is going to be the integral along dp of f of p n of p. Or, if you throw in everything that we've got, the pressure is equal to 1/3. So let's plug in what f of p is. This is equal to the integral of dp of n over delta x times p v times dp. So I just plug in this into there. Then I divide through by an area. And this turns into a volume. So I divide through by an area and my force turns into a pressure. I got a number density divided by delta x. That comes from my little test scenario. I'm going to divide by an area, and now I've got number density divided by the volume. So now I'm left with NP VP dP. So this pressure integral is important, because this thing is what is how you get a generic pressure from something that is complicated. How do I get the ideal gas law from this? To get the ideal gas law, we say that, okay, I can get rid of that, I don't need that. To get the ideal gas law, sorry, my camera wasn't pointed in the right spot. How do you get the ideal gas law from this? Well, the ideal gas law is the same as assuming that we've got a random well-behaved gas of clouds. So N of P is equal to what? It's equal to V squared e to the minus 1/2 mv squared over kT. And then there's a normalization out in front that looks like kT over m to the 3/2. The thing that matters, the important parts of the equation are the v squared here, the v squared here, and then the 1/2 and the kT. Make sure that the width is right. So this is the number of particles with, oh, I'm sorry, I wrote this as p. P squared over 2m. That's fine. I can do that. That's not illegal.
What's in front of V?
The bit in front,
Yeah.
that is the p squared over 2m that you need to normalize the equation. And I don't care too much about what that is. Look it up. Make sure that that makes sense. So it is kt over 2 pi m to the 3 halves. But I might have messed up the pi in there. The important bit, so we start with the Maxwellian. So this is the Maxwell-Boltzmann distribution. And I just plug that into here. I just plug in 1/3 times the integral from 0 to infinity of the Maxwell-Boltzmann distribution times v times mv times dv. And I can just do that integral. I can switch between p and m just fine. And I do that integral and I'm left with the ideal gas law. If I have something where my momentum distribution is not Maxwellian anymore, so that means something's on fire, it's exploding, it's colliding with something else, there's something weird going on, I can still get the pressure this way. I just have to do a little bit more math. So the pressure equation, I'm going to write the pressure equation last. You can close this, we're going to write this with the integral. 1/3 integral of n of v dp dp. Or p equals rho over mu times the mass of the proton times kt. Both of those are fine, depending on which one you need. What's that?
You put that way too low.
Sorry. That just says PV equals nRT at the bottom. Or in these other units, rho kt over mu m. Oh my! Oh, I still got 15 minutes left. Man, I talked way faster than I expected. Let's back up a bit. So we have mass conservation, we have force balance, and we have pressure. And the next two I didn't work up the lecture yet because I didn't think I was going to get that far. So bear with me. I'm going to go fill in a thing that I didn't do. I'm going to back up and do a thing that I was going to skip today because I didn't think I was going to have time. So we will flesh out. There's two more. Actually, let me write down the equations real quick before I move on to other stuff. So the last two equations. So now we've got mass conservation and force balance. We need to know where the photons come from and where they go. So let's talk real quick. I'm going to set up the next couple of readings. So how do we have a pressure gradient in the first place? What's causing the pressure gradient?
Mass stacked on top of each other?
That's a good guess, one.
Atmosphere to no atmosphere.
So that gives you a pressure gradient, but what's at the bottom of the star that's making it hot?
Nuclear.
The nuclear burning.
Like photon pressure.
Photon pressure comes into it, so photon pressure matters, but it makes heat, and the heat makes gas pressure, and the gas pressure is what holds the star up. So we got to figure out how that. So when you're trying to talk about what is the heat source, so and I'll do this in better detail on Monday. The first thing that people thought was, well, it's probably the gravity and the heat. Like I've got this massive stuff, gravity's pulling on the star and releasing heat. So if I say that the gravity pulling down is what's releasing the heat, then my gravity must go down with the luminosity of the star, right? So if GMM over R squared minus GMM over R, this is the potential energy, right? So this potential energy is going into the luminosity of the sun, and that's where the energy is coming from, then I can sort out how fast M and R, or M is conserved, but R isn't. So if photons are coming out, then L, which is, so let's see, the integral of L dt, so this is the total amount of light that has come off of the star, plus Gm over R squared. Oops, that's a minus. That's got to equal 0. So as this, so, or you could say the integral of L dt equals Gm over R squared, Gm rho over R squared. As this gets large, this also has to get large, and the only way for this to get large is for R to decrease, right? If that's the only physics that we have is gravity. So you can sort out how long will it take for my star to collapse to a point, and you get about 10 million years. So gravity can't be the only story. So this is called Kelvin-Helmholtz contraction. So the question is, what causes pressure? And gravity isn't it, because gravity would do it too fast. And this is the first thing the book does in this section, is he goes through the Helmholtz contraction time scale. And he shows that it's like 1 million years. And that's not very long, because we know that the sun is more than 1 million years old. So what we need to do is invoke nuclear burning. And nuclear burning, I'm just going to write the equation down. Heat production, dL, dr, well, L is the luminosity, equals, once again, 4 pi r squared times the mass density times epsilon is the energy per nucleon. How do you spell nucleon? N-U-C-L-E-O-N. Is that right? So epsilon is the energy you get per, and it might be per mass. So that's the energy per unit mass that you get from the nuclear burning. And it gives you a radiation gradient, dL dr is 4 pi epsilon. I'll derive that next week. But I wanted to state it. And then the last one of the equations is, okay, so the nuclear burning creates heat down at the center, and that heat is what causes the pressure. But the nuclear burning, how do things burn? How does a nucleus burn? Oh. What does a proton look like to another proton?
A waveform.
Let's talk about the electric field. If we think about the potential energy of a proton as it's coming at another proton. So what we need to do is so nuclear burning is taking 2 protons and smashing them together and making a helium. That's super oversimplified, but we'll go through the details of that. How does that work? So I have this Coulomb barrier. So this is a 1 over r squared barrier from the Coulomb force. So the Coulomb repulsive force goes like 1 over r squared, right? If I get close enough, the nuclear force takes over, and I get this negative bit real close. Right? So I have this wall that if I can get, so this is a proton, I have another proton, it's going to come this way. If I can get it over this hump and into here, then it's bound. Does that make sense? It's like golf. You just got to get it in the hole. But the hole has a huge wind that's blowing things away. So it's not like golf, it's like hard golf. And it's worse than that because this goes up to infinity at 0. So it's not like you can get over it. I mean, it rolls over, but you're really not going to get over this. What has to happen is this is a wave. This is an impenetrable barrier, but the wave can exist over here. So the wave becomes not real and tunnels through this barrier and jumps past it. Yeah. It just magics its way. I know, right? It just magics its way in. This is quantum mechanical time. This is a super real phenomenon. And you can see this in real life. You can see this in real life. So if you have...
this, you're not like leaving this behind anymore.
Was that...
He just said again.
Oh, did you do tunnel?
We just started in modern.
We just did it in modern.
Perfect. I think that this is... I probably should get the modern syllabus and see all the ways. Who's teaching modern right now?
No.
Okay. I should just get his syllabus and see all the ways.
He skipped quantum tunneling.
Okay.
But he went over it briefly.
Yeah, he was like, don't take any notes on this. I'm just going to tell you what it is. You don't have to know it really.
So long.
That's what I'm going to do too.
You don't have to know that you'll never be tested on it, just for fun, just so you know.
Okay. This is a little. I need you to know that it's a process that happens, but we're not going to worry about it. So let me tell you. Don't take any notes for a second. Let me tell you real quick what happens. So I got a wave function, and it oscillates, right?
I don't think we're at the level where we could actually get anything.
That's all right. So my wave oscillates, right?
Yes.
Because why? Because it's imaginary, or because because it's real. My wave oscillates. When I hit this barrier, the electric field can still penetrate into the barrier just fine. Like there's still some electric field there, even though there's not a proton. But if I can pick up and start oscillating again on the other side of the wall, I can do that. So you can see this. Are you familiar with total internal reflection?
Yeah.
Right. So if I have a prism and I have a light that comes in at the wrong angle, if it's steeper than the Brewster's angle, is it Brewster's angle? Whoever's angle, all the light is totally reflected. Was that?
So it isn't Brewster's an ice cream place?
It sure is actually. It's also an angle that at which
it's actually fire.
I love Brewster's. This is a good place. That's where I like to take my kids after they do something like have a piano recital.
They got really good mint chocolate.
It's really good.
Oh, they do. Stop. Go.
Really
Y'all
lost
wanted
it.
me.
Okay, total. So this process is called total internal reflection. And so why is that? So the electromagnetic field has to reflect all the way. There's no transmitted component of the electromagnetic field. There is a decaying component of the electromagnetic field that's out there, but it's not oscillating. So if I put another prism right here, that's close enough, then the photon can jump the gap and start propagating again. Does that make sense? Because the electric field, so my electromagnetic field oscillates like this, and then it just decays, and then it can start oscillating again once it's in this medium that it can propagate in, right? Was that?
Why it's still be oscillating the other way to be
Oh yeah, this is oscillating too.
Okay.
But when you put this up here, the transmission goes down, the reflectance goes down because some of it goes forward.
Isn't that the setup of the interferometer? Kind of. It's like two. Yeah, you run into similar kinds of geometry all the time. An interferometer is not a tunneling device. Actually, I don't know how a partially reflective mirror works as a quantum mechanical object. So I'm not going to answer that. I'm not going to say anything. So it could be.
So similar ideas. Okay, so what do I need? I need to make this happen. I need to hit the. So if I want to get a sizable number of nuclear reactions, I need to be hitting my protons together pretty hard. Not as hard as you might think, because we have this tunneling that will allow us, that lowers the actual barrier. But tunneling is a random process. It doesn't happen every time. So I need a lot of interactions, and they need to be high energy. So my density times my temperature has got to be bigger than some large number. So when my density is large enough, then the probability of running into something else is high. And if the temperature is high enough, then those collisions have enough energy to start to fuse. And there are several chains through that this goes through that we'll talk about when you get to the reading. We'll talk about that next week. And that gives us this equation here where epsilon, so now the gradient in the luminosity is going to be given by the production of photons, or the production of energy at the center. And I'll derive that equation in detail next week. And then the last thing, am I on time? Oh, great.
3 minutes.
Man, I had 10 minutes and then I rambled and now I'm short 10 minutes. I don't know how I did that. Time management is not my friend. So the last thing is heat transport. So how do you transport heat? You learned this when you were like 4th or 5th grade. And there I actually need, so a lot of times I'll say, oh, this is a thing you learned in kindergarten when I'm talking about calculus ideas, because it's hilarious. This is actually a thing you learn in like 4th or 5th grade. How does heat move from one place to another?
Conduction.
Radiation.
So conduction, convection, and radiation. The same is true in the sun. So this is just how you can move heat. This is the only ways you can move heat. So radiation, oh, we didn't talk about, I forgot to talk about the mean free, it's going to be a homework problem. It's how I solve the fact that I forgot to talk about it. How long does it take for a photon to get to the Earth?
A long time. From the center of the
From
sun?
the center or from the surface?
From, yeah.
So you guys did the reading. Okay, so from the surface of the sun, how long is it? 8 minutes. From the center of the sun, it's like 50,000 years. So, why? Because the mean free path is very short. It's a random walk. Did you guys watch Price is Right when you were sick, when you were a kid?
Yeah.
No? All right. And I don't know if it was still cool when you guys were kids, but it was the thing when I was a kid. They have this game called Plinko, which is like a bunch of little pegs, and they drop up. So there's like a bunch of pegs.
Yeah.
And you drop a disc, and it bounces around the pegs, and it gives you a Gaussian at the bottom. So that's the same process that's going on in the sun. The mean free path, which is the path that a photon can go before it hits something else, is only like a centimeter. So it has to bounce around an awful lot of times before it can actually leave. So radiation matters, but free streaming radiation isn't the transport mechanism in the sun. Conduction is relatively straightforward, and we kind of ignore it a lot. Convection is the hard one. So convection, I'm going to write the equations down, and then I'm going to run out of time. So when we talk about convection, we have to talk about thermodynamics, and we have to talk about the first law of thermodynamics, and we have to talk about what adiabatic means. And in my experience, by this point in your career, you're still a little dodgy on what adiabatic means. So, which is fine.
Hebrew?
Was that?
Was that Hebrew? Like you just said things.
Sanskrit.
Yeah, I know. Okay, so adiabatic is about entropy, so we got to talk about entropy too.
Oh.
Right.
I
Okay.
know enough to know I know nothing.
This equation's easy. This equation's easy. The equation's easy. The details are a pain in the ass. This equation's a pain in the ass, and the details are not quite as bad as nuclear burning. But we'll get it. It takes me a little bit longer so I'll write it down. What we're left with, and I'll write it down over here. Heat transport dt dr equals minus 1 over gamma times mu m h over k. That's just the proton mass. Times g m over r squared. Or, so this is for convection. And if you're in the radiative dominated regime, we're in minus 3 over 4ac kappa bar rho over t cubed times L over 4
Let's say 4 AC.
Yeah, 4 AC. So let me go through and derive all these things. Gamma is the adiabatic index. Don't worry, I'll explain it. A is the radiation constant, which is just the Stefan Boltzmann constant over C. There might be a 3 there now, I can't remember, because I forgot to write it down. And K bar is the mean opacity. So we have two basic ways that heat can move. So we have convection, or we have radiation. So, and conduction matters, but we'll talk about it later. So we have radiation where the photon's motion is what's doing it, and it's this random process, so it's long. Or you can just pick the stuff up and move it. So of the three, conduction, convection, and radiation, which one is the easiest way to get heat off of a thing? Convection. Almost always, unless your thing is like crazy hot. So radiation might be it. Convection is usually it. Way hot, way faster than thermal conduction. Thermal conduction is a very slow process. Convection is just picking all the crap up and moving it, so it's way faster. So I do this a lot. Similarly, in hydrodynamics, if you take a cup of coffee and you put a drop of cream into it, it'll take on the order of a couple of days for the molecular motions to mix the cream into the coffee. But you can do it in half a second with your spoon, right? You just mix that really fast. Convective mixing is almost always the fastest way to do things.
What is gamma?
Gamma is the adiabatic index. P equals rho to the gamma is that gamma. And if this isn't familiar, I will explain on Monday, because it gets into the.
Is that pressure or?
This is pressure, and this is density, and this is the adiabatic index. It's the ratio of specific heat. Man, gamma is this funny thing. It's a lot of things. It's the ratio of specific heats, but that doesn't really matter. It's the thing that goes in the index that tells you how squishy the gas is.
Squishy?
Yeah.
Squish.
Well, okay, if P equals rho to the gamma times to the 10th, then when I increase the density a little bit, I increase the pressure an enormous amount.
I see. Okay.
So I can't squish this,
Okay.
because as soon as I try to change the density, the pressure's right there jacking up my plant.
Okay.
But if I make this 1, then when I squeeze on it, the pressure doesn't really do very much, so I can squish it really hard. That is the squishability-ness that gamma is not something that you'll hear most of your other physics professors talking
No,
about.
that makes sense.
Because most of your other physics professors actually suck at thermodynamics. Sorry, I shouldn't have said that on record. I'm pretty open that the rest of my colleagues all suck at thermodynamics. I mean, some of them are fine, but some of them skip it.
You can strip it from the record.
Yeah. All right. That's all I got to say for